So it's great to be here, but I'm puzzled as to why. This is a series the philosophy department puts on called UW Philosophers Tackle Contemporary Issues, and if you look at the history up there, this was over a long time ago. But I'm kidding, of course. The principle of parsimony is with us still in contemporary science and in everyday life also. It's named for Ockham, a medieval philosopher, but contemporary science uses this tool in reasoning. Just a little vocabulary, parsimony. I have to tell this to my intro students, so I hope you won't mind me telling it to you. The word parsimony means an unwillingness to spend money or to use resources. So an example would be the cooks were parsimonious in their use of butter in the recipe. And the principle of parsimony applied to theories is the theories are better when they postulate fewer causes or processes or entities. And the goal tonight is to try to understand what makes this theory tick. So there's Einstein saying what I just said before. He thinks that Occam's razor is an indispensable tool in doing science. And the puzzle, as I say, is to understand why this much-used principle makes sense. And here's what I'll do. I'll give you just a tiny bit of history. It didn't start with Occam, the medieval philosopher. It started much earlier, maybe in Aristotle's own work. I'm going to give you just a tiny snapshot of one episode in this long history. And then for the rest, I'm going to talk about two frameworks within which the principle of parsimony, Occam's razor, can be justified. So in this time of the scientific revolution, we have great philosophers, scientists like Descartes, Leibniz, and Newton. And in those days, the distinction between philosophy, as we now call it, and science, as we now call it, was much blurrier and continuous. So all three of these figures did work that we now look back on as being both philosophical and scientific. So I'm going to say a little bit about one of these guys and give you a picture of how he understood Occam's razor, which was not unique to him. And then I'm going to fast forward to now and talk about a very different way of thinking about this idea. So here's Newton in his book, the Principia, the mathematical principles of natural philosophy, he called it. And he lays down 4 rules of reasoning there. I'm going to talk about 2 of them just to give you a flavor of how Occam's razor is part of the scientific revolution. So Newton says, we're to admit no more causes of natural things than such as are both true and sufficient to explain their appearances. Here's his justification in the Principia. To this purpose, the philosophers say that nature does nothing in vain. That's a little catchphrase from Aristotle. And more is in vain when less will serve. And here's some beautiful poetry. For nature is pleased with simplicity and affects not the pomp of superfluous causes. Isn't that great? The second rule is related. It says, therefore, to the same natural effects we must, as far as possible, assign the same causes. And the examples he gives are respiration in man and beast, the descent of stones in Europe and America, the light in our culinary fires and of the sun, and the reflection of light in the earth and on the planets. And what he's saying that is that when you have 2 systems that are observationally similar, you should try to explain them in terms of the same causes. Newton was famous for unifying the theory of motion in Aristotle, and after there were separate theories of motion, one for terrestrial motion, the other for celestial motion, totally different laws. And Newton's great achievement was to unify the theory of motion so it would cover both the motion of the moon and the falling of an apple. So unification is rule 2, and you can think of unification as part of the idea that simpler theories are better. A unified theory of 2 or more phenomena is simpler than a disunifying theory that gives a separate explanation for each little piece. So what's the justification? Newton says nature does nothing in vain. I mean, like, how do we know that? And he says, so what's the justification of thinking that nature does nothing in vain? Well, he wrote a book never published about interpreting the Bible, in particular the book in the Christian Bible called the Book of Revelations. And it tells you how he really thought of Occam's razor in science and also in biblical interpretation. For Newton, these were not separate problems. He wrote more about alchemy and religion than he wrote about physics, as we would now call physics. And for him, the rules of reasoning are the same both for biblical interpretation and observations as interpreted by science. So this is what he says about revelations, but you'll see science coming into this. He says, to choose those interpretations which without straining reduce things to the greatest simplicity. Truth is ever to be found in simplicity and not in the multiplicity and confusion of things. As the world, which to the naked eye exhibits the greatest variety of objects, appears very simple in its internal constitution when surveyed by a philosophic understanding, so it is in these visions, the visions reported in the book of Revelation. So we should interpret visions in the same way. And how do we do the two tasks, interpreting the Bible and interpreting observations in science? Here's the key. It's the perfection of God's works that they are all done with the greatest simplicity. He is the God of order and not of confusion. And therefore, as they that would understand the frame of the world must endeavor to reduce their knowledge to all possible simplicity, so it must be in seeking to understand these visions. So here's the picture that Newton and many other of these 17th century geniuses who created the scientific revolution, this is how they saw the world, that God created the laws of nature. He also built us to have the minds we have. He made the laws of nature simple, and he gave each of us a taste for simple theories. We prefer simple theories over complex things because God gave us that preference. And the result is that our thinking and the way the world is, the simplicity of nature, fit together. So this is Newton's justification for Occam's razor. The justification is nature is simple. And how do you know that? Because God made nature. That's why it's simple. And we seek out simple theories because God built our minds that way. So that is the theological setting that so many people in the 17th century had of the justification of the principle of parsimony. Well, here we are in the 21st century, and what I'm going to talk about tonight is what you ought to think about Occam's razor and its justification if you set aside this theological story that was so influential in the 17th century. How could you justify a preference for simple theories without bringing God, the designer of the universe, into your story? In the 20th century, a lot of progress was made on this problem, and I'm going to describe two lines of inquiry that I think help us really understand this in a totally different way from the way Newton, Leibniz, and Descartes thought about it. So here's the basic question, which we want to make precise. Why should you think that simpler theories are better than theories that are more complex? And one obvious answer is, well, we should ask better. Simple theories are easier to understand. They're easier to remember. They're more beautiful. That's a sense in which simpler theories are better. It's correct, but it really misses the hard problem that is involved in thinking about the justification of Occam's razor. The hard problem, there are several, are like this. So what? Simpler theories are beautiful and easy to understand. Tell me why I should think that simpler theories have a higher probability of being true. Tell me why simpler theories are better supported by the evidence we have, or possibly tell me why simple theories are more predictively accurate than theories that are more complex. So the hard problems about Occam's razor have to do with the relevance of simplicity to thinking about the way the world is. And you're not addressing that question by talking about yourself and the fact that you like simple theories, that you can remember them well, that they're beautiful to you. That is not on topic. So these three problems are the hard problems, and I'm going to be talking about ways of solving these two of the three. Now, I'm going to get a little mathy, and I bet a lot of you are math phobic, but I'm going to try to make it, without numbers and calculations, give you a feeling for some mathematical ideas from the theory of probability that will help you get a grip on ways of thinking about Occam's razor and connecting it with those two questions about its justification. So bear with me, take a deep breath if you are math phobic. I hope I can communicate the basics here without making it a blur. Okay, so this is the only picture in Darwin's Origin of Species. It's a picture that biologists would now call a picture of a phylogenetic tree. At the top of the page are species that exist now. As you go down the page, you see present-day species tracing back to common ancestors, and those common ancestors tracing back to still older common ancestors. And Darwin thought that everything alive on our planet traces back to one or a few common ancestors. Current biology doesn't hedge and say one or a few. The standard picture in evolutionary biology now is that all life traces back to a single common ancestor. And so I want to start thinking about Occam's razor in the context of this idea of common ancestry. So let's think about what kind of evidence would be relevant to justifying the hypothesis of common ancestry that Darwin endorsed and that contemporary biology continues to endorse. So here's an example. Let's work with an example. So human beings and monkeys both have tailbones. And is that evidence that they have a common ancestor? Is that similarity evidence for common ancestry? Well, first I want to get you to have a feeling of how that question is connected to a question about parsimony and simplicity. Well, if human beings and monkeys had a common ancestor, then it's possible that tailbones evolved exactly once in the history of those two lineages. They go back in the past, and was retained thereafter. On the other hand, if human beings and monkeys had separate ancestors, then tailbones would have to evolve separately once in each of those lineages. So there seems to be a difference in how many changes need to occur in the history of these lineages if you're going to get what you observe now, that present-day monkeys and human beings have tailbones. So it's in that sense that Darwin and biologists now especially think of the common ancestry hypothesis as simpler, as more parsimonious. The common ancestry hypothesis requires fewer originations of new characteristics than the separate ancestry hypothesis. But our question, which will be repeated several times, is, okay, so what? It's simpler, it's more parsimonious, but why is that a reason to think the common ancestry hypothesis has a better claim on being true of the world we live in? What does parsimony have to do with the world that we live in, as opposed to our subjective preferences? Okay, here's some terminology, but it's a terminology about probability, but nothing hard. So we're going to use O for observation and H for hypothesis. And this symbolism here with O vertical slash H, the probability of O slash H means the probability that O has on the assumption that H is true. And the terminology out there in probability and statistics is really horrible, because the terminology is the probability of O given H is called H's likelihood, whereas the probability of H given O is called H's probability. It's the worst possible terminology, because in ordinary English, for something to be likely and for something to be probable mean exactly the same thing. But the mathematical genius R.A. Fisher chose this terminology 100 years ago and it has stuck. So unfortunately, we have to use this. I'm going to be especially interested in likelihoods, and I'll be using that word 25 times. But I want you to make sure you understand what I do and what the world of probability and statistics understands by likelihood. It means the probability of an observation given a hypothesis. How likely the hypothesis is not how probable it is. Rather, the likelihood of the hypothesis has to do with how probable the hypothesis makes your observations. So just to crystallize that distinction, and maybe this will be the only thing you'll remember in an hour or two, I hope not, is here's a simple way to keep the difference between the probability of O given H and the probability of H given O really clear in your mind. Here's the example. So let O be the observation that there are noises coming from your attic, and let H be the hypothesis that says that there are noisy gremlins bowling in your attic. I hope you see that the probability of O given H is high. But the probability of H given O, I hope none of us thinks that's high. So this is an example which sort of crystallizes the idea that to talk about the likelihood of a hypothesis is a whole different question from talking about the probability of the hypothesis. And I'm going to be talking about likelihoods now. So here's an idea about the interpretation of evidence that is not totally uncontroversial, what is in philosophy, but I like it, and I'm going to be using it. I'm going to try to jolly you into thinking that it's a sensible principle, and then I'm going to use it to think about Occam's razor in connection with the example of human beings and monkeys both having tailbones. So here's the principle I want to use. It says that we have some observations and two possible hypotheses. And the idea is that the observations favors the first hypothesis over the second exactly when the observations are more probable if the first hypothesis is true than the observations would be if the second hypothesis were true. And here is the example that's supposed to make you all think, oh yeah, that's a good principle. So we have an urn. It's filled with balls. Each ball has one color. And we're interested in testing two different hypotheses about all these balls that are in the urn. The first hypothesis says that 80% of the balls in the urn are green. H2 says only 50% are. And we're going to test these two hypotheses by drawing some balls out of the urn. We're going to draw 100 out. And suppose it turns out that 90 of the balls drawn are green. Now, that doesn't prove that one of those hypotheses has got to be true and the other has to be false. But I hope you'll agree with me that the observation is pointing in the direction of one of those and away from the other, that the observation favors one over the other. And I hope you'll furthermore agree that the observation favors H1 over H2. If H1 were true, it's not that surprising that you would get these observations. If H2 were true, it's rather more surprising, much less probable that you get those observations. So this is supposed to be an illustration that gets you to think, yeah, the law of likelihood, that's a cool way to understand how you interpret observations as they bear on competing hypotheses. But what is this going to have to do with the problem we started with, the problem of understanding why common ancestry and separate ancestry will not only differ in parsimony in their explanation of why human beings and monkeys have tailbones, but why that's a significant fact about them, why there's something better, in some serious sense of better, about the common ancestry hypothesis versus the separate ancestry hypothesis. And to answer that, so here's what we want to, first of all, there's the if that we want to get clearly in mind. If I can show you that the observed similarities of human beings and monkeys is more probable under the common ancestry hypothesis than it is under the separate ancestry hypothesis, then the law of likelihood is going to take that inequality, that greater than thing that we have in the yellow box, and conclude, oh, that means the observed similarity of human beings and monkeys favors common ancestry over separate ancestry. So that's got an if in it. And we have two questions we want to think about. First of all, why should I think that the observed similarity of monkeys and human beings is more probable if they have a common ancestor than it would be if they only had separate ancestry? Like, why is that first inequality is true? Why is it true? And what we're looking for is assumptions that seem reasonable and plausible that will tell us that that inequality is true, and then we'll have our answer. But what are those assumptions? And then separately, maybe there's some other assumptions which will have the opposite significance. It'll tell us that no, under these weird assumptions, these different assumptions, the observed similarity is more probable under the separate ancestry hypothesis than it is under the common ancestry hypothesis. So notice how the inequality flips here, greater than, less than. So we're looking for assumptions that will justify the first inequality, but we want to be alert to the possibility there might be other assumptions that justify the second one. Well, one of my heroes in philosophy, Hans Reichenbach, created this principle called the principle of the common cause. He didn't talk about common ancestry, but we can adopt what he's doing, adapt what he's doing to the issue of common ancestry and separate ancestry. Because after all, when you say that two things have a common ancestor, when you say that human beings and monkeys have a common ancestor, you're talking about some organisms or organism who's a common cause of the characteristics that human beings and monkeys have. And similarly for the hypothesis of separate ancestry being a hypothesis of separate causes. And it turns out that Reichenbach described assumptions that suffice for the common cause hypothesis to have the higher likelihood. And these assumptions are often very plausible. They're used pervasively in evolutionary biology. And I'm not going to tell you what the assumptions are. If you want, in the Q&A, I'm happy to describe what they say. But all I want you to get so far is there are these assumptions that seem reasonable to lots of people, in at least a lot of settings, which have the consequence that that top inequality is true. That under those assumptions, the common ancestry hypothesis makes the observed similarity more probable than the separate ancestry hypothesis does. So we've got the common ancestry hypothesis having a higher likelihood in the technical sense of likelihood that we're using. Okay, that's nice, isn't it? But the assumptions aren't like written in granite. They have to be true in every possible situation. You can tinker with Reichenbach's assumptions and create a situation in which you get this flip happening, so that under these different kinds of assumptions, it turns out that a similarity has a higher probability under the separate cause, the separate ancestry hypothesis, than it has under the common ancestry hypothesis. So let me describe a couple of those weirdo cases. So before I do that, here's the picture. Nice Reichenbach assumptions that tell you that the common ancestry hypothesis makes the similarity of human beings and monkeys more probable than the separate ancestry hypothesis has. That's nice. But now change those assumptions and you can get the reverse kind of result. And I'll describe some examples. 2. Okay, suppose there is a gene that doesn't make you sterile, but it makes you have very low fertility. Your chance of having a kid is extremely low. Now imagine the two individuals in some population both have that gene. I think that's evidence that favors, that's evidence against their being siblings. Because if they were siblings, how did their parents produce 2 kids? Whereas if they're not siblings, then it's more probable that each of them would have it. So this is a case violating Reichenbach's assumptions, where it turns out that a similarity can favor separate cause over common cause, unlike the Reichenbachian assumptions, which tell you that common cause is more likely than separate cause. That's the one example. Here's a second one, not about biology at all. Suppose that each of several businesses has one boss, has a single boss and multiple employees. And suppose in this bunch of businesses you look at 2 employees, X and Y, and it turns out they're similar in a certain way. They're both unhappy with their jobs. Is that shared characteristic evidence that the 2 employees have the same boss? That would be the common cause hypothesis. Well, maybe sometimes, but not under some assumptions. Here's an assumption that wrecks that conclusion. Suppose that if X's boss is strict, this raises the probability that X will be unhappy, whereas if Y's boss is strict, this lowers the probability that Y will be unhappy. It turns out that with that assumption in place, the observed similarity, X and Y are both unhappy with their jobs, favors separate bosses, not the same boss. It's not, maybe, I hope it's a little intuitive. It's not obvious why that works out in the mathy background that I'm not really giving you, but it's true. Okay. So let me sum up what I just said about parsimony and likelihood. So we have these 2 hypotheses, a common cause and a separate cause hypothesis. And we have an observation that 2 objects, they could be 2 species, 2 employees, whatever, have a trait in common. And in the common cause, in the common ancestry example, you see how the common cause hypothesis is more parsimonious. And given Reichenbachian assumptions, it'll turn out that the common cause hypothesis has a higher likelihood. And I claim that this answers at least part of one of the hard problems. One of the hard problems I had up there before was why I think that simpler theories are better supported by the evidence. Well, the simpler theory, the common cause hypothesis, is better supported. It's favored by the observations with these assumptions in place. But it's not always true that when X and Y share a trait, that always favors common cause over separate cause. There are ways of violating the Reichenbachian assumptions that give you that weird flip of the inequality sign. Okay, so that's one one way of justifying Occam's razor. What's great about simple theories is not just that they're beautiful, not just that they're easy to understand, but in a rather general setting, simpler theories are better supported by the evidence than more complex theories. So that's a reason to take parsimony and simplicity seriously here, I claim. Here's a different problem which has to be looked at, I think, in a totally different way. We're going to talk about, is there ever a general thing you can say about simple theories being more predictively accurate? I mean, that would be a reason to care about them if you have a stake in making accurate predictions about the future. And if simpler theories were more predictably accurate, that would be worth knowing. And that's, as I keep saying, not a different kind of thought than saying, oh, simpler theories are easy to remember and more beautiful. So what about predictive accuracy? Here's the example I want to use to explain the sort of second paradigm for thinking about parsimony that's out there, thanks to work in the 20th century. So you drive south from Madison, you stop your car, you get out, and you see that on one side of the road is a giant field of corn plants, and on the other side of the road there's a second giant population of corn plants. Each of those populations has its own average height. Thousands and thousands of corn plants in each field. So you being an empirical scientist, you sample 100 corn plants from population 1, 100 from population 2, and you get your samples, you get the mean height of 56 inches and 52 inches. That's your data. And you're going to use the data you just collected from these 100 corn plants from here, 100 corn plants from there, to try to evaluate two models. The null model says that the mean height in the first population is identical with the mean height in the second. That's why it's called a null hypothesis. It's saying the difference between the two populations is 0. And then there's this model called diff, which just says that there exists a number beta such that m1 minus m2 is equal to beta. Beta could be positive, it could be negative, it could be 0. So diff doesn't commit to very much here. Null is a more assertive kind of hypothesis. As I say, if null is true, diff has to be true. And here's some terminology from statistics. Null has no adjustable parameters, whereas diff has a single adjustable parameter. That's what beta is. Beta is like this blank. You could replace beta with 35, you could replace it with 4, and so on. So what we want to talk about next is what it is to fit models to data. What that means is that you replace the adjustable parameters in a model with estimates of their value. So diff says that beta is m1 minus m2. What's the best estimate of the value of beta given your observation that in the samples you got 56 inches in one sample, 52 inches in the other sample? Well, the maximum likelihood estimate, the estimate that makes your observations most probable, is you should guess that it's 4. Notice that if that were true, if 4 inches were the real difference between the populations, it's not that surprising that you get these observations, whereas if you say that that beta is equal to 100 inches, it's kind of weirdly improbable that you actually got this data. So 4 seems like a reasonable estimate. So we've now fitted the two models to data. We didn't have to do anything to null because it has no adjustable parameters. Diff had one adjustable parameters. We've now adjusted it. It's gone. It's replaced by its best estimate. Okay, that's nice. So what? Now here's the prediction problem. You're going to go back to these fields and gather 100 corn plants from each of them. That'll be your new data. And I want you to think about which of these two models will do a better job of predicting what the new data looks like. You know which of them fits the old data better. You've got the data right in front of you, but you haven't looked at the new data yet. So how are you supposed to go about thinking about which of these models will be more predictively accurate? That is, do a better job of predicting data you do not have in front of you yet, but you will. You know from before that diff is fitting the data, the old data, a lot better than null does. But on the other hand, null is simpler because it doesn't have any adjustable parameters. Diff has a single adjustable parameters. And so now we're going to go along with this idea that's so common in science that simplicity in a model has to do with paucity of parameters. The smaller the number of adjustable parameters, the simpler the model. And again, we're going to ask that relevance question. Okay, null is a simpler model. It has fewer adjustable parameters because 0 is smaller than 1. But like, so what? Why is that relevant to the question of figuring out which of these models is going to be more predictively accurate when I look at new data? Before I give you the surprise, the mathy surprise about how to think about this, I want to describe an experience that scientists have all the time when they're working with models of data. Here's the experience. A really complicated model, which has lots of adjustable parameters, will do a great job of fitting the data you have already. But when you use that model fitted to the old data to predict new data, it often does poorly. So fitting old data, yeah, it's good to be complicated, but predicting new data, not so much. On the other hand, simpler models usually fit the old data less well than complicated models do. That was true in our example of null and diff. Yet when those simpler models are used to predict new data, they often do a bit better than their complicated competitor models. So that's just an experience that scientists have. Who knows why they're having that experience? But at least it suggests the idea that when you're thinking about evaluating models for their predictive accuracy, it's not just fit to the old data that you should be thinking about. Parsimony seems to be relevant. But like, why should it be relevant? Maybe it's just like this brute, inexplicable mystery. No. We have this guy, genius statistician from Japan named Akaike, who invented ideas that led others to invent this idea called AIC, the Akaike information criterion. The reason the AIC was invented is that Akaike proved a theorem. This is the mathy part. He proved, based on some assumptions, you always need assumptions to prove stuff, that an unbiased estimate of the predictive accuracy of a model is equal to, forget about the log thing, the probability of the data given the fitted model minus k, where k is the number of adjustable parameters. So what the theorem tells you is an unbiased estimate of predictive accuracy should attend to how well the model fits the data. That's what that red term over there is all about. But it also should attend to how complicated the model is, how many adjustable parameters it has. And you see that minus sign there. There's a penalty. Complicated models are penalized when you estimate their predictive accuracy because k is big. They have a lot of adjustable parameters. Simpler models pay a smaller penalty. Right. And k, wasn't k what we said we mean by simplicity of a model? The parsimony of a model is how complicated. What does that mean? How many adjustable parameters it contains. That's why null is more parsimonious, simpler than diff. And here's a thing from mathematical statistics that tells us that parsimony matters in estimating predictive accuracy. It's not just an aesthetic frill. No, it's actually relevant to judging which models will do better at predicting and which worse. Now, the AIC framework and other ideas in this part of statistics called model selection theory don't say the simpler theory is always better. Because, of course, notice that there are two things that are relevant to evaluating a model. Not just how simple it is, but how well it fits the data. And there's a kind of conflict or trade-off between those two considerations. Complicated theories have better fit the data, but simpler theories have lower values of k. Okay. But what is true in the AIC framework is that if you have two models that fit the data about equally well, then AIC is going to tell you that the simpler model will be more predictively accurate. Here's one more wrinkle about AIC, and I'm done telling you about it. And by the way, in terms of the mathy hard part, you're well over the hump now, okay? Here's a weird thing about this example, and it's not unique to this example. before you even look at one corn plant drawn from either of these populations, I think you know, with about as much certainty as you know anything, that null is false and that diff is true. Remember what diff says? It just says there is a number which is the mean height in the first population minus the mean height in the second. How could that be wrong? Whereas but null says something very specific, says the difference is exactly 0. Thousands of corn plants over here, thousands over there, and null is saying that the difference in the mean height, it's not like within 10% of 0, it says it's 0. So why do scientists bother testing null against diff and examples like that if we know from the get-go that null is false and diff is true? Well, the answer is, if they care about predictive accuracy, the fact that null is false and diff is true doesn't settle the question that's being asked. It doesn't tell you which of those will be more predictively accurate. And one of the philosophically interesting things about this area of statistics is that it often turns out that simpler false models are more predictively accurate than more realistic true models. So that's why it's not crazy to test these two things. If your interest is in predictive accuracy rather than truth, then by all means you got to do it. AIC said you got to do it. Okay, now I've talked about two frameworks for justifying Occam's razor, for justifying the principle of parsimony. One was the Reichenbach story about likelihoods, common ancestry versus separate ancestry. When will the common ancestry hypothesis have a higher likelihood than the separate ancestry hypothesis, given that humans and monkeys both have tailbones? First story. Second story was null and diff, and I was describing how Akaike and the AIC show you why the number of adjustable parameters is relevant to estimating the predictive accuracy of a model. So they're really very different ways of thinking about Occam's razor, very different frameworks, but they have a couple things in common. First of all, neither of them says, oh, parsimony, there's no justification for parsimony. It's a rock bottom thing. We love it for its own sake. It doesn't have to be connected with anything more fundamental. Neither of them is saying that. They're both saying the justification for Occam's razor is that simpler theories deliver something that we care about that's more fundamental. Greater likelihood in the case of Reichenbach, greater predictive accuracy in the case of Akaike. And the second similarity between them is the justifications, the Reichenbachian justification of common cause being better than separate cause, and AIC's and Akaike's theorem, they all depend on assumptions. And if you change the assumptions, you get a difference in the outcome. So both of them involve conditional justifications of Occam's razor. It's not like you can say, no matter what the world is like, simplicity is a good thing. That's not what's going on in these two frameworks. Okay, that's how they're similar. How do they differ? Well, we have likelihood being the story that's going on in the Reichenbach common cause, separate cause thing, whereas in the AIC thing, we've got the complexity of a model being relevant to estimating predictive accuracy. But here's a way to sort of crystallize how they're really about different things. Reichenbach's framework is all about which hypothesis, the common cause or the separate cause hypothesis, fits the data you actually have in front of you. It's about fitting old data. That's what this likelihood comparison is about. Whereas AIC is all about predicting new data. So the whole problem that's being addressed is different between these two frameworks. Now, these are really different, and no one in statistics or probability or philosophy, I think, has seen a way of unifying these two justifications of Occam's razor. So as of 2015, I think we're in a situation where Occam's razor is broken into pieces, and understood in this way it has that kind of justification, understood in this way it has a different justification. That could all change tomorrow, but I think that's how things are right now. And the other thing I want you to notice about this is I've never said that these are the only two possible justifications for parsimony. Maybe there are other ways to justify Occam's razor beyond the Reichenbach likelihood story and the Akaike story about predictive accuracy. And that leads me, so I want to sort of speculate a little bit about this last possibility. Maybe there are examples of good parsimony arguments in science which cannot be captured either in the first way or the second way. So in closing, I want to describe an example that might be of that sort. So I went to a lecture a couple weeks ago about why the dinosaurs went extinct. And it was a rather surprising lecture. The lecturer started off by describing the conventional explanation of the extinction of the dinosaurs, but then he said, I have got a far more parsimonious explanation of the extinction. It's better because it's more parsimonious. So let me describe each of the theories in turn and how the lecture developed. So he started off by describing the conventional theory. The conventional theory is a giant meteor crashes into the Yucatan Peninsula, which sends up a dust cloud, which blocks the sun, which makes all the grass and vegetation die. So the dinosaurs had nothing to eat, and so they went extinct because they starved to death. That's the first explanation, and the lecturer then says, that's what everybody else thinks, but I have a simpler theory. And his theory was this. In a galaxy far from us, there was an advanced civilization which built giant spacecrafts which they sent to Earth in large numbers. And when the aliens got to Earth, they walked out of their spaceships and they noticed these beautiful animals, dinosaurs walking around. And they thought, these are so fantastic, we should take them back to our home planet. So the aliens, they had big spaceships, and there were a lot of them. They loaded all the dinosaurs on Earth into these spaceships. This is a theory. And they were about to take off when one alien said to the other, you know, we don't need to take all of these dinosaurs back to our planet. We'll just take a small breeding population back. That'll work. So they offloaded most of the dinosaurs, and then they took off and went back to their planet. The lecturers paused there and looked around, and someone in the back row raised her hand and said, but wait a minute, why did the dinosaurs go extinct then? And the lecturer said, oh, I forgot a detail in my theory. After the aliens went back to their planet, a giant meteor hit. So that wasn't my story. That was from Saturday Night Live, as told by Guido Sarducci. I wish I didn't have the nerve to give you the story with Guido's accent, but anyhow, that's where it came from. So here are the people in Madison who helped me put these ideas together. Thanks.
Discussion. Welcome, first of all, Elliott. Thanks a lot for joining us.
It's my pleasure to join you
yeah.
At your meeting.
Yeah, and so Hannah, go ahead with your question.
Hi, thanks for the talk. So I work on ideological parsimony in metaphysics of science, and especially with a deflationary approach. And my question is about the notion of cause and underlying reality when it comes to simplicity. So I can understand from a scientific perspective why the possibility of a singular cause would be quite attractive. But the way in which cause figures in biology might be very different from how it sort of figures in physics, and so also in economics or psychology. So I want to ask you, assuming that it is not simply an aesthetic preference, what warrants the belief that there is an underlying reality which might be a singular cause? Like, do you feel that this might in itself be an unparsimonious assumption, since it is more of an aspiring ideal than something that our current evidence warrants? So yeah, if you want, that's my question. Thank you.
Thanks for your question. If you have a bunch of observations and you have a unifying theory that deals with them all, and its second theory, which is a disunifying theory that gives a separate explanation for each single observation, for one observation each, the unifying theory is simpler, more parsimonious, let's suppose. And from the AIC point of view, you may be able to show that the first theory has a higher estimated predictive accuracy. So that would be one way to deal with this. And the logic of AIC, and it's also true for the Reichenbachian story about common cause versus separate cause, there's nothing specifically about biology or physics or economics or any science that's part of the underlying assumptions, the methods are therefore very general. So as soon as you can satisfy relevant conditions, you can show that the more parsimonious theory has a higher likelihood, or the more parsimonious theory maybe will have a better AIC score. So I view these as very general things. That said, there are concepts of parsimony that by design apply only in a restricted subject matter. So cladistic parsimony in evolutionary biology is like that. It's about genealogical hypotheses in which an ancestor gives rise to many descendants, and you have a branching phylogenetic tree. You have evolutionary processes like drift or selection going on in the branches of the tree. And there's no pretense that this concept of cladistic parsimony would apply to theories that don't have to do with genealogies or branching causal structures. It's very specific to that. And, you know, I guess I can't think of an example, but I wouldn't surprise me if in other sciences one finds highly specific concepts of parsimony that really don't have this generality. And of course, they invite the question, okay, let's think about what the justification is here. You mentioned at the start, I think, I thought you were going to go over into the metaphysics, And as you know, many metaphysicians now and in the past have used parsimony to justify one ontology rather than another. And I think it's a very interesting question whether any of the concepts that plausibly characterize the way parsimony works in empirical science carry over to metaphysics. I mean, I think a lot of metaphysicians think that some parsimony makes sense in science, we can use it in doing metaphysics, and we're just being scientific. But if the concepts are very different, maybe that has to be rethought.
Thank you, Elliott. I actually do argue against using and using it across in metaphysics. But thank you so much. I'll probably drop your mail about this. Thank you.
Okay, sure.
Thanks, Anna. Gurmeet, you have a question?
Hello, sir.
Yeah.
Can you hear me?
Yes, please go ahead.
Yeah. So I was actually thinking about machine learning. Like the name of the game in that area is essentially prediction, right? And in that also, number of parameters actually increases overfitting. The problem you talked about, that fitting the old data not necessarily means the new data will be get fitted as well. Right? That's known as overfitting in machine learning. But there's really interesting phenomena that not just more number of parameters, the same number of parameters with higher values actually overfit more. To actually reduce that, we use something known as lambda smoothing. That will go into maths of it, but the thing is that higher parameters actually overfit more than low values of parameters. So in that sense, the whole description of the model, including the size of the parameters, actually can be counted as, okay, the smaller the description, better the theory, something like that, from the point of view of Occam's razor.
That's interesting, and I'm not aware. I wasn't aware of what you just described. I'm not aware until you told me about it. That's interesting. As you said, AIC doesn't pay attention to the values of the estimates of parameters. It's just you count the number of parameters. That's the only way parsimony enters into AIC. Maybe what you're describing is an improvement on AIC. I don't. Nothing that I hope I've said about AIC would carry the message that AIC is perfect. There's nothing could possibly be better than it. I mean, in my book, I talk very briefly about something that's more general than AIC. It's called TIC, letter T, named for Takeuchi, another Japanese statistician, who developed a model selection criterion.
I can't hear it.
Elliott, I think we've temporarily lost Elliott.
Oh
yeah. Okay, you're back now. I think we can hear you.
Okay, so I was just describing TIC, the Takeuchi information criterion, which is more general than AIC. So that's an improvement on AIC in a certain sense because it requires fewer assumptions than AIC does. So I'm surprised to hear that fact you reported about the size of the estimates being relevant. Interesting. Thank you for that.
I do have a few other questions, but maybe later.
Yeah,
But,
please
just
just raise your hand again if you have another
yeah,
question. I'll
yeah,
come
of
back to you.
course. Yeah, of course. Just to complete this, actually, not just lambda smoothing. In machine learning, there are a few other ways as well, because of which Occam's razor comes in. For example, something known as transfer learning. So if you actually, if you think that that can be included.
Maybe it's.
Can you hear me?
Yeah, I think Gurmeet has been lost this time. Okay, all right. So maybe Gurmeet, I think we lost you.
Oh,
But
okay.
yeah, maybe
Yeah.
we can come back to you. We can come back to you after this round of
Yeah,
questions
sure.
are done for your next
Yes,
question.
yes,
Okay.
of course.
Okay. Okay, Prashanta, please go ahead with your question. Prashanta, can you hear me?
Yes, I can. Do I need to start video or I don't need to do that?
No, you don't need to if you don't want to, but you're welcome to.
Hi, Elliott. Can you hear me?
Yes, I can. Hello, Prasanta.
Hi. So I have actually a question about your last reference to the dinosaurs story, but regarding these two approaches to one is likelihood and other is the AIC. So at least in the AIC or any other, the dependence on the assumption, how good are those assumptions? They are extremely important. And so that definitely we need to take into account and these are important.
I agree with you completely, Prasanta. It's important, and I think scientists sometimes forget this, and of course, so do we philosophers, that every theorem is based on assumptions, and it's only as good, the theorem is only as good as the assumptions are. So we have to scrutinize this and be careful that the problem, say in science, that we're applying AIC to, or any other method for that matter, plausibly satisfies the assumptions. And if it doesn't, you have to ask yourself, well, why am I entitled to use this method? I think that applies to the Reichenbachian common cause stories too. I mean, if certain conditions are satisfied, the common cause will have the higher likelihood. But if not, maybe not. You have to pay attention to whether your example satisfies those assumptions.
So your last dinosaur story, you said here are the two approaches before you introduce the story, two approaches to simplicity problem, but no unification is made or no connection is made. And then you told the story about the dinosaur. So how that sheds light on those two issues? You know, could you please just say a little?
Yeah, that was supposed to be kind of a joke. I think there's a third parsimony paradigm that I mentioned briefly in a few places in the book, but I don't really make a big deal about them. And that's a case where parsimony, where the more parsimonious theory has a higher prior and posterior probability. And maybe that can be applied to the dinosaur case. If you think of the conventional story as telling a story about the dinosaur, about the meteor hit, and the crazy story that's invented by Guido Sarducci, it's got the meteor story, and it adds all this nonsense about aliens and blah blah blah. It's still got the meteor hit in it. So if you like, the conventional story says X is true as a cause, and the Guido Sarducci alternative says X and Y are together the explanation. Well, X has a higher probability than X and Y, and no matter what the evidence is. So maybe this is an example in which we can use the probability of hypotheses to say there's a difference between these two stories. It's not a difference in likelihood. They both predict, you know, what we observe. There are no dinosaurs.
Thank you.
Maybe something like that.
Okay. Thank you, Prashanta. Vishy, you have a question? Please go ahead.
Am I audible?
Yes, you are. Yeah.
Hello, sir. Could you please give a summary of any of Reichenbach's assumptions in his principle of common cause, which, when challenged, flip the mathematical relation and preferring the opposite hypothesis over the original one?
Right. It would maybe help if I put a slide up here.
Yeah.
Can I share a screen?
Yeah, you can share your screen. I think, Don, can you make, I think you might need to be a host. Don, can you make, yeah, you're a host now, so you can share your screen.
I think I have this ready. I hope I have it ready. Should I try now?
Yeah, please.
Okay. Yeah, this should be it. All right. Okay, so I have to now, I've lost my controls here. Oh boy, what did I do wrong? Oh, I see, I found it, sorry. Yeah, I got it. Go back over here. All right, now I'm gonna share a screen.
You were sharing a screen a second ago. I think you unshared.
Oh, I was? Okay, well,
Yeah.
I'll go back to that. Okay, okay. So here we are. So you can all see that, yes?
Yes, you can see.
Okay, now let me find the relevant slide. Oh, here we are. Okay, so at the top you see the Reichenbachian assumptions. I hope I've understood the question, so this is actually relevant to it. There they are. And it turns out that if you violate one or the other of these assumptions, you can find situations where the separate cause explanation has the higher likelihood. Would you like me to walk through the explanation of what these assumptions say? Is that what the question
Yes, sir.
was?
If it's I mean, if it's too much trouble, then could you please?
No, it's not trouble. So the first assumption, let me get my cursor out here. Branches are not 0 and not 1, but they're somewhere in between. Let's remember what these letters mean. So P is the probability that human beings will have a tailbone if this ancestor had a tailbone. A is the probability that humans would have a tailbone if the ancestor did not have a tailbone. And similarly, Q is the probability that monkeys have a tailbone if the ancestor does. B is the probability that monkeys would have a tailbone if the ancestor does not. Little c is the probability that this ancestor will have a tailbone, and so on. Well, I guess I've covered all the parameters here. Okay, so that's that. So what does this mean? Let's just consider this the case where P is greater than A and Q is greater than B. That's the one that's plausible in this example from evolutionary biology. So the probability that humans have a tailbone is greater if this ancestor already has the tailbone than it would be if the ancestor lacked a tailbone. P is greater than A here. And this is a general idea about evolution in these kinds of cases. The probability of a descendant having a characteristic is greater if the ancestor already has it than it would be if the ancestor lacked that characteristic. And, I mean, you could probably make up examples in which that's wrong, but it's a really plausible assumption in lots of cases. All the models, the kind of probability models of evolution that phylogeneticists use work this way. They have this as an assumption. So the second one is very probable. The third one says that the probability that both humans and monkeys would have a tailbone given that the ancestor has a tailbone is simply the product of the probability that humans would have a tailbone given the ancestor state times the probability that monkeys will have a tailbone, again, given the ancestors having one. That's what conditional independence means. That's the definition in probability theory. And then this is a kind of fancy name for a kind of simple idea. You can see that all the 5 letters that are used over here to describe the common cause hypothesis just get transferred over here. So the probability of humans having a tailbone, if you start at the bottom, is going to be a function of C, P, and A. And you can write out the algebra that describes that. And exactly the same thing is true if you're over here. The probability of human beings having a tailbone is a function of C, P, and A, and it's the same function. So one of the kind of perhaps puzzling or well, certainly important features of the example is the probability of each observation that humans have a tailbone is the same here as it is there. And the probability that monkeys have tailbones has the same value here as it has there. But, and this is the important point, the probability that they'll both have tailbones is greater over here than it is over here. That's a structural feature. So let's see now. Okay, so this is one kind of problem for the Reichenbachian assumptions. There's a gene that causes an individual to become sterile after it has one baby. And suppose individuals X and Y both have that gene. That's evidence against there being siblings, which would be the common cause hypothesis that I want you to consider. And what's being violated here is this kind of conditional independence. The probability of monkeys having a tailbone, given the ancestor is in some state, is the same as the probability of monkeys having a tailbone given what's going on here, and given that human beings also have a tailbone. That's the idea that this screens off this from this. A less technical, but maybe more intuitive example is this one about the businesses where each business has one boss and several employees. We look at 2 individuals, X and Y, and the thing that's peculiar about them is that if X's boss is strict, that raises the probability that X will be unhappy, but it lowers, for Y, it's the opposite. If Y's boss is strict, that lowers the probability. And what we have here is a violation of this second condition.
Okay.
That condition says that if this ancestor is having a tailbone raises the probability of human beings having one, it also raises the probability that monkeys will have one. Because if P is greater than A, Q has got to be greater than B according to the Reichenbachian assumption. Let me add an idea that's not in the slides you were already looking at. Let's violate this first assumption by having 1 for C, little c, 1 for P and Q, and 0 for A and B. So the probability that human beings and monkeys will both have tailbones is 1 according to the common cause hypothesis, and it's also 1 according to the separate cause hypothesis. Probability is 1 that this guy will have a tailbone, and then if this ancestor has one, the probability is 1 that humans will have it. So we have a likelihood equality when we violate this first assumption in the way I described.
Yes, sir.
I hope that addresses your question.
Yes, sir. Yes, sir. Thank you. Thank you.
Okay, thanks, Vishy. Vipul, you have a question? Please unmute and ask.
Yeah. So
I'm going to stop. Shall I stop sharing the screen? I guess I could do that.
Yeah, sure. Yeah. I mean, it's,
Okay.
yeah.
Okay.
okay, yeah, thank you for the lecture. Given that there's this split in how we understand parsimony, what does that do to the relationship between prediction and explanation? Is there a trade-off between them, or is it just two different domains, and depending on the goal of your research, you choose one or the other meaning of parsimony? Thank you.
If it, you'll remember that Hempel said that every explanation makes a prediction, and every prediction is an explanation. He got into a lot of trouble for this, at least the second of those, and in fact the first also, thanks to Wesley Salmon. Here's a way they come apart that is surprising, I think, and it comes out of the AIC framework. If the story explains something, the story has to be true. Hempel had that condition. I think most other philosophers go with the idea that a story can't explain something if the story is in fact false. It could be explanatory in the sense that it would explain it if it were true, but if it's actually false, it doesn't actually explain what you're observing. So explanation requires truth, maybe, let's suppose that's right. But the thing that's so surprising about the AIC framework is that you can recognize that theories known to be false can be good predictors.
Yeah.
Because they contain, and the reason they're false is they contain idealizations.
Yeah.
So that is a kind of wonderful thing that kind of comes out of the predictive accuracy idea in AIC.
Okay, thanks, Vipul. Jyoti, please go ahead.
Hello, Professor. Thanks for the talk. So in model selection theory, when we want to evaluate using different models for predictive accuracies, there seems to be an important underlying implicit assumption, which is like no matter how complex the phenomena be, it can always be reduced to a simpler theory, can be put into these models, and the parameters can be adjusted and can be then translated into an elegant theory, like Newton's unification theory. So something more needs to be said about this as well, that we understand that simple theories have higher probabilities, but is there any exception involved in this?
Let me start with the first part of your interesting question. Model selection theory doesn't say only consider simple theories. It doesn't say that the simple theory will always be the best predictor no matter what the data say. Remember, in AIC, there are these two terms that go into the AIC estimate of the predictive accuracy of a model. The first one is fitting the data. The second one is how simple the theory is. They both matter, and a complex theory that fits the data a lot better than a simpler one will get a better AIC score. That can happen, and it does happen in science. So it's really, the framework doesn't prejudge whether the simpler theory is going to be better. You have to look at the data and see how well each model fits the data. So I hope that addresses the first part of your question. The second part, I'm a bit reluctant to bring the probability of theories into this problem because I don't see a way to assign prior or posterior probabilities to lots of theories like Newton's theory or Einstein's theory or Darwin's theory. So that's why I'm kind of, that's maybe the simplest part of my reason for not being a Bayesian through and through. I think there are cases where you can assign good objective probabilities to hypotheses. Take the case of medical diagnosis. Someone takes a tuberculosis test, it comes out positive, and you want to figure out what the probability is that the person has tuberculosis. Well, if you know the person comes from a certain geographical region, and you know how frequent tuberculosis is in that region, the frequency that we know about from data can be a reasonable prior probability for the person's having tuberculosis, and then use Bayes' theorem and you can get the posterior probability, the probability that she has tuberculosis conditional on the positive test result. So I have no problem with that. So for contexts in which we can justify the assignment of prior probabilities and not just say, oh, it's my subjective confidence. That's how I feel. I'm fine with Bayes' theorem, but I don't think that's true for these big scientific theories like I mentioned. Sally has tuberculosis, it works for that.
Okay, thank you. Ravid, you have a question? Please go ahead.
Hi, thank you. Yeah, so my question is about, I guess I'm thinking about our ability to use simplicity to choose between theories or something like that. And or parsimony. So you mentioned a few different senses of parsimony, I think. And I'm kind of wondering, like least number of causes or like less number of parameters. And I'm wondering whether whatever theory we come up with, we can come up with a story as to why it is simple. And so maybe simplicity is more about a way we prefer to present things, or like a way about how we end up presenting things, but not necessarily something about how things are in the world, because maybe, yeah, we can always present things in the world in different ways and then come up with a story as to like why it satisfies this criterion. Yeah, what do you think about that?
I agree that sometimes when we talk about one theory being simpler than another, that may not be epistemically relevant. It might just simply reflect how easy it is for us to understand the theory, or how easy it is for us to test the theory, how easy it is for us to solve equations maybe, and possibly, plausibly, I would say, that does not bear on anything about the way the world is. It doesn't bear on whether the theory has a higher likelihood or a higher probability, or will be a better predictor. It's just a kind of fact about what we like. I mean, maybe it's just an aesthetic thing. I mean, that would be an example of what I'm talking about. It has no bearing on what we should believe about the world. But, we like simple theories. We think they're beautiful and convenient. So that can certainly happen. But just as we should not assume that simplicity is always epistemically relevant, we should also not just assume that it never is. And when we come up with a puzzling case, this is an invitation to do an analysis of some sort. So so suppose, I thought this was hinted at by part of your comment. Okay, you might say, when you got the Reichenbach common cause versus separate cause thing, I see, given the assumptions that the simpler theory has a higher likelihood. I see when you have a model selection problem, you're interested in predictive accuracy, and you satisfy Akaike's assumptions, you can use AIC to estimate predictive accuracy. You could grant that. But look at this example where Reichenbach's assumptions don't hold, AIC doesn't hold, but yet it looks to us intuitively that one theory is simpler than the other, and we'd like to know, is that epistemically relevant to something like likelihood or predictive accuracy or probability or whatever you want to call it. Let's do some research. I noticed, I hadn't remembered this, but when I tuned in a few minutes before 8:15, I noticed that towards the end of the lecture, before I get to Guido Sarducci, I am not claiming that the only justifications of parsimony are what I just told you about, the one from Reichenbach, the other from AIC. Maybe there are other parsimony paradigms that we would need to develop, and this is an invitation for other work. I mean, there's work in other parts of statistics and so on that I didn't talk about. I would never claim that these are the only two possible justifications for thinking that parsimony is epistemically relevant.
Okay, thank you. Ganesh, please go ahead.
Yes, maybe there would be some change in the topic, but I'm talking in the philosophy of mind area. So we have this problem of mental causation, where we have two competing causes that overdetermine the causal pathway leading to action. So simple way to set the stages: physical brain states leading to action and psychological mental states. So one overdetermines the other, and through Occam's razor, we kind of erase out the psychological mental explanation. So the question that I want to ask is, when do we say simplicity is not the best thing, and we do need to choose other epistemic virtues like novelty or applicability to human need, relevance and context? So how do we determine this, choosing other epistemic virtues over simplicity? Could you please enlighten?
Yeah, I'd like to start with the really interesting example you describe about the puzzle in philosophy of
Am I
mind
audible?
about whether,
Yeah, you are audible. Yeah. Go ahead, Elliott, sorry.
the question about mental causation. I wanted to mention this article that I co-authored with Larry Shapiro called Epiphenomenalism, the Do's and Don'ts. It's on my website if you'd like to have a look at that. We think that the mental cause hypothesis and the neurophysiological hypothesis are not in competition, and they may well both be true. And I think it's a kind of misapplication of Occam's razor to say, look, Occam's razor tells us that one cause is always better than two. Therefore, I have to choose, and I'll come up with something. Maybe I think, why do I say, and then what I think people are inclined to do there is say, if I have to choose one, I'm going to go with the neurophysiological cause because it's somehow deeper or more naturalistic or whatever. Maybe it's physics envy. I don't know what it is, but you don't have to choose. I mean, and the starting idea here, look, we all know that there are lots of true descriptions of the causes of events. Some are more complete than others. Some are more general than others. They're all true. So there are lots of, so just restrict yourself to the, I mean, think of an example about why somebody crashed their car. Well, there are lots of contributing causes, and it's I think it's just a misunderstanding to say, well, no, Occam's razor says we have to choose one of them. So it was either the fact that the roads were slippery, or the fact that the driver was not paying attention, or the fact that the tires on the car were worn out. tell me it's only one of those. No, maybe they're all three there, and they're all contributing causes. I mean, this is a familiar everyday thing, and I think we have to hold on to that simple idea when we think about the problem of mental causation and resist the idea, oh, Occam's razor says we have to choose one of them. Well, no, maybe but several descriptions of the causes are correct.
Okay, thank you. Darshi, you have a question? Go ahead. We can't hear you for some reason, Darshi. You're not muted, but we still can't hear you. I don't know why that is. Maybe your mic is not set up correctly, or maybe you need to unplug your headphones or something. I don't. We still can't hear you. Maybe you can type out your question if we're not able to hear, and then you can I can read it out. Yeah. Yeah, you're not audible. Sorry. Yeah. So let me move on to the next question, and meanwhile, maybe Darshi, you can type out your question or something. Yeah. Don, go ahead.
Yeah. So my question is, when you started your talk, you started with these historical examples. So you mentioned Descartes, Leibniz, and Newton. Have been described two of Newton's four rules of reasoning, which is about philosophers, what they say that nature has nothing, does nothing in vain. And I was wondering why you omitted reference to Aristotle, who also says something along those lines. And I mean, it was a little surprising because Aristotle is a philosopher of biology, and is there a reason why you did not? Or I would just like to know what you think of Aristotle's principle of parsimony.
Yes, Newton's borrowing a phrase from Aristotle when he says that nature does nothing in vain. I don't know why I left it out. Maybe I just left it out because I had, a short length of time assigned me to give that lecture that you saw. In the book, I talk about Aristotle's formulation, and that's a short version of a paper I wrote with my colleague Paula Gottlieb on what Aristotle meant by that, which I think is quite fascinating, and it's not what Newton meant by it. I think, Newton, and to this day, we think of nature as the name for the totality of what happens in space and time. When Aristotle was talking about nature, he was talking about the individual natures that each organism has or each being has. So it's in the nature of tigerhood to have claws. It's not in the nature of tigerhood, of a tigerhood, that tigers should be able to play chess. So it's the idea of human nature, the idea of objects in general, each having essential properties. That's what Aristotle, I think, is really talking about there. And it's a totally different concept of nature, I think, from the one we use when we talk about natural science. Nature is just whatever happens. You don't have to be an essentialist to talk about nature, but you, I think, do have to be an essentialist to talk about Aristotelian natures.
Okay, thank you. So I'm still waiting for Darshi to type out his question. So in the meantime, let me ask a question. I don't think I fully understood either of the two arguments, but in keeping with my advice to ask one question at a time, I'll focus on the second, the AIC version of simplicity. And so the argument there was that the model with fewer adjustable parameters has greater estimated predictive accuracy, right? Something along those lines. I guess my worry was about that. I'm not sure how that maps onto our ordinary notions of simplicity. So here's how I'm thinking about it, right? So if you have sort of a simple curve fitting problem, and so you have a family of models which are kind of straight line models, and then you have a family of models which allow for all kinds of squiggles. It's true that the first family had fewer adjustable parameters than the second, but I don't associate a theory with a family of models, right? I would, so you pick out one squiggly line and one straight line. They both have no adjustable parameters, right? All the parameters are fixed. Now, I guess you could say that the squiggly line has more fixed parameters, but once you're looking at fixed parameters, that just depends on the coordinate system you choose, right? You could express the squiggly line with fewer fixed parameters using a different coordinate system. So I guess what would you say about that? Yeah.
Okay, so let's use the word model to describe things that have adjustable parameters, and theory to be propositions that have no adjustable parameters. And you can, of course, as you said, construct a theory from a model by fixing the values of the adjustable parameters in the model, so you then have a theory. That, I mean, we could use that terminology. And AIC, then the AIC story about why parsimony is relevant doesn't apply to theories. Because, as you say, they have the same number of adjustable parameters, namely 0. Scientists often investigate models and use them to make predictions. So there's a place for models in the sense I'm describing in science, and that's what AIC is talking about.
So would you, maybe one way of thinking about this is, tell me if you think this is accurate, that instead of thinking of simplicity as a feature of theories the way they've traditionally been understood, these sentential constructs, think of them as features of like the search process for theories or something like that? Would that be a better way?
No, it's a theory. I mean, models are propositions. Those adjustable parameters, I mean, a good way to think about what they mean is they are tied to existential quantifiers. So the diff model about the 2 fields of corn says there exists a number called alpha, which is the difference between the mean height in the first field and the mean height in the second field. So that's a proposition. It's an existential claim. It's maybe a little surprising that we have a theory that doesn't have a universal quantifier, and it's got an existential quantifier. But it's models. That's what models are. If models means adjustable parameters. I wanted to the last part of what you said. I wanted to make a comment about that. So one thing I didn't talk about in the lecture at all, and I don't spend much time on it, I mentioned it a little bit in the book, is what is a parameter? Now, you might think that a parameter, when we're counting parameters, this is an artifact of the notational system we're using. That if we set up our language one way, we'll get 38 parameters. But if we redefine some stuff, we can maybe reduce that to 4 parameters. And in fact, there are tricks in, I don't know what area of science this is in which you can take any bunch of parameters, any numbers you like, and express them as a single number by this technique called interleaving. But anyhow, so you might think that counting parameters, that's going to be linguistically variant, and anything interesting about inference should not have a dependency on the choice of a language. Okay. A good, that's a kind of foundational question about what is going on in AIC and related statistical frameworks, where you're paying attention in some way to the number of adjustable parameters. And let me just give you an analogy, which I think is relevant to answering this question and arriving at the conclusion that a parameter is not an artifact of notation. This is not supposed to be a convincing argument, just a suggestion for a way to think about maybe being able to get that kind of view developed. Consider the difference between a circle and a sphere. And I think we would say that circles are 2-dimensional figures and spheres are 3-dimensional. So we have 2 dimensions in one and 3 dimensions in the other. Is that merely an artifact of notation, or is there some sort of serious mathematical reason why we should think of circles one way and spheres in another. And there's a kind of, there's a mathematical theory that sort of helps you here, I think.
All right, thank you. Yeah, that's interesting. Okay, Gurmeet, you have another question you wanted to ask? Please go ahead.
Yes, yes. In nervousness, I actually forgot to thank you earlier.
I'm sorry, your voice was breaking up and I didn't hear what you just said. So would you start again, please?
Thanks.
Gurmeet, there's a problem with your connection, I think. We can't. Can you hear us? Okay, I think we've lost Gurmeet temporarily.
Lot for such a wonderful talk. Hello?
Oh.
Hello? Hello?
Hi,
I can hear you now.
Yeah, yeah, go ahead, Gurmeet. Yeah, go ahead. No, I think we've lost him again. Yeah, Gurmeet, sorry, but we keep losing you. So again, I think like Darshi, if you'd like to type your question out in the chat, I can read it out to Elliott. But for now, I'll just move on.
Yeah, yeah. So yeah.
Oh, okay. Gurmeet, are you there? Hi. Okay, all right, let's move on. Vidyadhar Rao, you have a question? Please unmute your mic. Yeah.
Thanks for a good lecture. So my primary question is actually to understand the applicability of this Occam's razor. So I would like to understand, or I mean, it would be good if you can clarify me. Occam's razor, is it applicable only in the statistical settings where there are predictions, there are uncertainties about the input that the model gets, okay, and then we make hypotheses about the observed data or based on the assumptions on the causes. So that is one way to look at the space of problems which we want to solve, purely based on prediction problems which have some historical data, and then we build models which can explain the future inputs. Okay, but then on the other side, when we come back to computer science and more formal theory, formal methods, where we have seen methods like which are based upon purely logic based reasonings, for example first order logic or higher order logics, where we were able to create, I mean, or at least there is a research area which creates automated theorem proving, where a computer can automatically generate a theorem, can automatically verify a proof, and then perform a deductive reasoning to get a proof out of it. But then the recent developments, if I look back at some of the, I can't recall because I'm not an expert in that area, but then the proof of, I mean, in such kind of automated theorem proving areas, the length of the proof is actually very, very long. It could be some billions of bits or bytes, or it can be measured in terms of memory, or maybe if you write it on a paper, it could be the longest proof that has ever been generated by a computer when compared to a human being. So how do you differentiate Occam's razor in these two areas? One is the prediction kind of setup, and the other one where we have a dedicated problem, well-posed problem, which we require a proof where a computer will generate a very long reasoning to confirm it.
I would describe, you're right that the two parsimony paradigms I've described involve theories or models that confer probabilities on observations, and we want to understand whether simpler theories are better in some sense, either in terms of likelihood or in terms of AIC. In a purely mathematical setting, I wonder if parsimony is epistemically relevant. That is, I understand the example is familiar to me about how some machine generated proofs are very, very long. That's inconvenient for us human beings, but that's not a reason to doubt their truth. I don't see. So we'd like to get shorter proof so we can understand things, but this is not, of course, this is a perfectly legitimate goal that research mathematicians would have to get a simpler proof. But it's not a judge, as far as I understand your question, it's not a judgment about whether the proof is actually correct. It's a pragmatic virtue that we want proofs to be short and clear and easy to understand if possible. But to me, I would put that into the same category as the aesthetic value we put on simplicity. On its face, it doesn't look like it has a bearing on what's true. So I'm not saying that comment sort of covers all of mathematics. I can imagine mathematicians being in the following situation. There's an open conjecture. No one has a proof or a disproof of it. And scientists might be inclined to use how simple the conjecture is versus its negation as some sort of useful heuristic thing for inclining you to think that maybe that proposition P is a theorem versus not P, and possibly find that a useful heuristic. So maybe before we get to the having a proof, we go through all sorts of informal reasoning and search strategies where simplicity plays a role in them, maybe.
Okay, thank you. Okay, Gurmeet might be back, so let Gurmeet try again, and we'll see if your connection works this time. Can you unmute your mic?
Hello, is it stable now?
Yeah, I think we can hear you now.
Yeah. First of all, thanks a lot for such a wonderful talk. I forgot to thank you earlier in nervousness. I was wondering about the Solomonov induction-based proof of Occam's razor's prediction power. Essentially, Solomonov proved that there is a way to mathematically quantify the notion of Occam's razor. And that was essentially, as you mentioned, that it is pretty hard to set prior probabilities for these theories, right? So he actually based his idea based on some earlier maths from Kolmogorov and devised a method to formulate a prior probabilities. And that is known as algorithmic probability theory, and that actually have higher prediction power. It can be proved that Occam's razor formulated in that fashion actually gives higher probability for new data. It has low overfitting. So like at least that is one way to actually assign prior probabilities for any theory whatsoever. So what do you what do you think about that?
To be honest, I remember reading Solomonov's work years ago, but I'm afraid I don't remember anything in the way of details here. But I will say that a purely mathematical way of assigning prior probabilities, it reminds me of Harold Jeffreys' work 100 years ago, where he described the simplicity postulate, which involved proposing a simplicity ordering for differential equations and then telling you to give the simpler ones higher prior probabilities. I see no justification in doing that. There are other ways of assigning prior probabilities besides that one. So that's what bothers me about making up prior probabilities. Now, that said, some assignments of priors will of course have different effects on inference from others. Certainly that's right. But why that's the right thing to do to me is a mystery. That's why I just don't put much stock in the Bayesian approach. So, but I'm sorry I can't answer in more detail because I don't remember my Solomonov.
So, there is one theorem in Solomonov induction that it has a sort of completeness, that if data has any pattern whatsoever, then given enough time, Solomonov induction will pick it and predict based on that. So essentially, given enough time, the prediction is the best theoretically in Solomonov induction. That seems like good enough reason to actually believe that as a good prior probability, that best prior probability to predict the future data, right?
That sounds like the more or less traditional Bayesian idea of the washing out of priors. So you and I have different prior probabilities, and given some assumptions about the problem we're working on, it'll turn out as we gather more and more data, and of course agree about how the data should be interpreted, our posterior probabilities get closer and closer together, even though we started with priors that were very different. That's true, but that doesn't show that the prior probabilities don't matter, because the theorem is asymptotic. It describes what happens in the limit. Right now we have, I mean, go back to the tuberculosis test coming out positive. We have one datum, and what your prior is that Sally has tuberculosis will have a profound effect on the posterior probability. And the fact that if we had 1 million observations, we would agree on the posterior probability. That's not relevant to the actual finite data set we have before us. So that's why the sort of Bayesian asymptotic result to me is not persuasive.
Gurmeet, were you adding something, or okay, I can't hear you anymore. I think maybe, so I don't hear Gurmeet.
Actually, the theorem is given enough. Yeah. So I was saying the theorem is given enough time, not given enough data. Even the data set is just 10 data points.
Okay, that's a different point then. I shouldn't have brought up the Bayesian
Even then,
thing
the prediction will be yes.
Yeah, I think
no, it's not the Bayesian thing.
Yeah.
Given really small data set, even then, given enough time, given enough learning, it.
I think we're losing you again, Gurmeet. Okay, I think we're gonna have to move on.
Will pick any pattern whatsoever if there's.
We've lost you again. At least I've lost you. I think what Gurmeet was saying there was that it's based on time, it doesn't require an infinite amount of data. And I think the idea is that the completeness theorem places an upper bound on the cumulative error of the process. It doesn't say that there's a limit. It just places an upper bound on it. So that's the.
Okay. Well, I have to confess I can't comment on that because I don't know my Solomon well enough.
Okay. All right. Darshi, I think you're maybe back, but I don't know if we can hear you now. Can you speak and see if we can hear you? No, it's not working. Sorry. Yeah. Prakash Tanabal. Mr. Prakash Tanabal, are you there?
Okay.
Yeah.
I'm sorry.
Yeah.
Thank you, Professor Sobers. Now, my question is kind of, I want to look at the slightly bigger picture, broader picture. What I really wanted to know if the Reichmannian distinction between discovery and justification still holds. My question is based on that. So I want to know if much of the discussion has been in the context of justification. So when you look at discovery, does the principle of parsimony, play out differently? And maybe in a context where we are assuming that we know the solution, but in the case of discovery, we don't know what the solutions are. Like the example you just gave about tuberculosis, we know that tuberculosis causes, that the bacteria causes, mycobacterium causes tuberculosis. But when we had this issue about gastric ulcer, the conventional understanding was acidity produces the ulcer, and there was an uphill task for people to prove that the Helicobacter was the cause, the bacteria was the cause of ulcer. You had this difficulty in making that switch because these two are two different kinds of causes. So I'm looking at, so there are issues that, are there some presuppositions before we actually talk about the success of science, or are we looking at something more broader as how science progresses? Does it have that kind of implications too? So.
Good. So using the Reichenbach's distinction between the context of discovery, the context of justification, I would locate what I was saying about common cause and separate cause and predictive accuracy solely within the context of justification. You've already got some theories you want to consider and you're comparing them. The discovery of the theories in the sense of making them up is done. And now with these theories, you want to know which is better in terms of likelihood, which is better in terms of predictive accuracy. There is a separate subject, which I didn't talk about except for like a paragraph in the book, which is about parsimony as a search strategy, where you start with a simple theory, and if it works, you stop. But if it turns out to be unsatisfactory, you then move to constructing a more complex theory. And if it works, you stop. But if it doesn't, you keep. So you start simple and build up to more and more complex theories if you have to, but if you don't have to, you don't do it. This idea has been explored by philosophers of science. It's completely different from what I was talking about. It's nothing, but they're both interesting things to think about.
All right.
So so the thing that and the thing that is you can probably sense from this thing I'm describing is there is a logic to the context of discovery. It's not this sort of irrational creativity thing that is being investigated, but a kind of methodical procedure that if you use it, good things will happen. So one of the results that's out there in this literature is if you start simple and go to the next simplest theory only if you have to, is that you'll have to change the number of times you'll have to change your mind about what's true will be minimized.
But does it work as some kind of a skeptic heuristic in the way you discover entities? I mean, that
I think it's only, to me, it's a way of, what I was just describing, it's a procedure for thinking up theories. It doesn't say the theories you're inventing are true or probably true. It doesn't have, or will be predictably accurate. But starting simple and then going to things that are more complex may have some pragmatic utility. Here's a context in which this is an old idea. Popper had the idea that simpler theories are more falsifiable than more complex theories. So it takes less data to falsify them if they are false. And that suggests a heuristic where you start testing the simple ones because a small data set will tell you that it's wrong if it's wrong. And only then do you go into more complex theories which require larger and larger data sets.
All right, thank you.
Okay.
I think I can come on now. You hear me? Okay, very quickly. Okay, Elliott, thank you. My question is the usual fossil question about history. I'll put it very briefly. It seems like, I think you already answered that a lot of time Occam's razor is being forced. I think putting it as parsimony is good. It's a guideline. It's not a meta law of theory. Okay, and I think Prakash's question is also related to that. So I often read things like Occam's razor is violated. I don't know what that means to say it's violated. I just quickly go and read from Ockham because I'm going to Ockham through my teacher Paul Spade in his Cambridge Companion to Ockham. So there are two places where we have Occam's razor. Plurality is not to be posited without necessity. Okay, now what is meant by necessity needs to be cashed out. And when a proposition is verified of things, more things are superfluous if fewer suffice, and so on. And then Paul Spade concludes from this, the razor is thus power for actually powerless for actually denying the existence of certain kinds of entities. All it does is prevent our positively affirming their existence. So maybe bosons could not be, posited affirmatively, right, until a certain point. So what I want to say is what is sold as Occam's razor is quite deviant from what Ockham was actually saying in a maybe not in a general way, but I think you preempted that by going back to Aristotle as far as the overall principle of parsimony. So my question is, if it's a guideline, it's not a law, and it should not be forced. That is my question.
Okay. So in the book, I draw a distinction that was not in the lecture that you watched. It's the distinction between what I call the razor of silence and the razor of denial. And I think what you were just describing is an interpretation of Occam's razor, which Occam formulates, where it's not denying the existence of anything. It's saying, I'm not going to postulate that. I'll be silent about whether X exists. I'm not going to say X does not exist. So that's a very important distinction. In the book, I have a little section about Occam himself, and I think I found a case in which he is actually using the razor of denial. It's not just being silent about things, but actually denying that this thing exists because it's not needed to explain anything. But those are very different principles. They raise different questions about justification.
Okay, thank you. So there are still have come to the end of our session for today. So I'm sorry that if I wasn't able to get to your question. Thank you, Elliott, for being with us for so long and for such a wonderful, productive discussion. And thank you for the great lecture. Thank you all for asking questions, for the great discussion, for sticking with us for this long period. Before I let you go, let me just remind you that we do this every week. We'll be back next Saturday with Paul Humphreys. So please join us for that as well. I'll be sending out a mail about it shortly. You can sign up for the mailing list by going to our website. With that said, I will close the discussion here. Thank you to all of you, and see you next week, hopefully. Thanks.
Okay. I enjoyed the discussion. Thank you.
Thank you.